The next topic we're going to look at is multicollinearity.
So in multiple linear regression model, where we have several x variables, if two or more x variables are highly correlated among themselves, then we call that multicollinearity. And multicollinearity actually poses an issue for the multiple linear regression model. There are several consequences, and these consequences can make the model unreliable or not useful or misleading. So the first consequence is that when there's multicollinearity, the t-test may turn out to be insignificant, while actually the variable is highly correlated with y. So let me remind you what t-test is about in multiple regression model. So in multiple regression model, we perform t-test to check if each of the x variables are highly correlated with y. Okay, and we say the t-test is significant if the coefficient is significant different from 0, and that means that corresponding x variable is highly correlated with y. Okay, so that's the t-test. But then when there's multicollinearity, although for a particular x variable, our intuition tells us this x variable should be highly correlated with y, but when we run the regression model, it turns out that the t-test is not significant, suggesting that this x variable is actually not highly correlated with y, which is counterintuitive and also misleading. And the reason being is not because the data tells us this x and y are not highly correlated. It appears to be x and y are not highly correlated because there's multicollinearity. What we will see is that when we perform the f-test to check if the model is valid, the f-test will pass, meaning the p-value for the f-test is less than 5%, and we will conclude that the model is valid. But when we check individual t or individual coefficient, we find none of the coefficient is significant, meaning that none of the x variables are highly correlated with y. And this contradicts to the conclusion of the f-test. Whenever that happens, the cause could be multicollinearity. The second consequence is probably more misleading and more serious. That is, the sign might be the opposite from what is expected. Intuitively, we expect one particular x variable to be positively related with y. But when we run the multi regression model, the model shows that they are negatively correlated. It is counterintuitive, and it could be wrong as well. And this negative correlation could be the result of multicollinearity. Okay, so these are the consequences. Of course, the first question is, how do we know if there's multicollinearity? One way to check that roughly is to look at the correlation coefficient matrix that we talked about at the beginning of this chapter. When we look at the correlation coefficient matrix, we can pretty much tell which x variables are highly correlated with each other. That give us some clue about the multicollinearity. And the other measure that is available is called the VIF, variance inflation factor. This factor is a more rigorous or more accurate measurement of the multicollinearity. And the idea is that if the VIF is greater than 1, that suggests there's a potential problem. And we usually say there's a potential problem is because this greater than 1, this threshold is not a very stringent threshold. The idea is the higher the VIF, the more serious the problem is. And as to when we believe it's a serious problem, when we believe it's not, this is also where experience and personal opinion comes in play. It depends on the situation, depends on the model. It also depends on the experience of the researcher and a lot of other factors. But in general, we will consider multicollinearity when we see VIF greater than 1. That's a general guideline. So let's take a look at it. So it says here, a large component of the cost of owning a newspaper is the cost of newsprint. Newspaper publishers are interested in factors that determine any newsprint consumption. In one study, data on annual newsprint consumption, which is the Y variable, the number of newspapers in a city, the logarithm of the number of families in the city, and the logarithm of total retail sales in the city were collected for cities. So as you can tell, the Y variable is newsprint consumption. And we have three X variables. Number one is the number of newspapers in the city. The second is the log of the number of families in the city. And the third one is the log of the total retail sales in the city. And intuitively, they should all be highly correlated with the newsprint consumption. On the right-hand side, without really going to Minitab, because we've already learned how to do the multiple linear regression model, so I'm going to skip that part. It shows the result of the multiple regression. We are more interested in this area or that table where it shows the coefficient for the X variables, the standard error of the coefficient, t-test statistic for the t-test. P is the p-value that we use to perform the t-test for each individual coefficient. And lastly, we also have VIF, just the measurement we were talking about, that measures the multicollinearity. Now, we're going to focus on this section. By the way, just to verify, first of all, the F-test, which is right here, the p-value for the F-test is 0. Basically means the F-test is passed, the regression model is valid. So we're good with that. Now we go to the individual t-test and look at each individual X variables and each individual coefficient. So we're going to start with the number of newspapers. For this one, the coefficient is 2385. If we look at the t-test statistic t-test, p-value is not less than 5%, meaning that this X variable is not highly correlated with Y. And you will find the same for the rest of the two X variables. It turns out this is exactly the situation I was talking about. You have a valid F-test right here, but none of the t-test is passed, meaning that none of the X variables is highly correlated with Y. That means although the F-test tells us the model is valid, if we look at the individual X variables, none of them are useful in predicting Y. So it turns out our model is not useful in predicting the Y variable. The cause of the issue is right here, these two numbers. The VIF for number of family and the retail sales is very high, 7.4 and 8.1. As we just talked about, for VIF measure, the higher the value, the more serious the problem is. Now 7.4 and 8.1 is much higher than 1. So we can definitely tell these two X variables are highly correlated with each other. That means we have serious multicollinearity. And even by intuition, if you think about it, the number of families in the city is highly correlated with the retail sales. That's for sure. So when you include both of them in the model, they will cause the problem. So what do we do if we observe the multicollinearity? Well, here's one potential solution. Of course, there are other solutions. Most time we will say when we have multicollinearity, we need to check the model specification. We will need to check the data. One solution that we can do is to drop one of the X variables that are highly correlated with each other. Okay, so we have two here, number of families and total retail sales. So we need to drop either one of them here. So the question is, which one do we drop? Sometimes people look at the p-value and we drop the one with the higher p-value. So between number of families and retail sales, the number of families has a higher p-value of 0.44, which means this variable in comparison to a certain extent is kind of less useful or important than the next variable, retail sales. So we're going to drop the number of families and keep the retail sales and rerun the model. And the results is shown here. Now let's take a look at it again. We're going to go to F-test, still valid, okay? We're going to go to the p-values for the t-test. And this time you can see that retail sales is highly significant, which is with a p-value of 0.001. That means retail sales is highly correlated with newspaper consumption, which makes sense. But still, the number of papers in the city is still not significant, meaning that this variable is not highly correlated with Y. Now, in terms of VIF, okay, it turns to be 1.7 this time. Now, let me go back just to mention this quickly because I didn't do that. Going back to the first round of the estimation, the VIF for papers is 1.7. Some of you may say, well, wait a minute. You said VIF greater than 1 means there's a potential problem. That is true, but I also said the threshold of 1 is not very rigorous, right? It's almost like for a general guideline. So in comparison, the next two VIF are much higher, so we don't consider 1.7 a big issue at this point. Same for the next page. When you have VIF of 1.7, that's not a huge issue, actually. So we will consider this model to be valid. Of course, to verify if we can use the model for forecasting, there are several other things we need to check, like the residuals, the adjusted R-square, etc. And that's the routine job that we always do using any multiple linear regression model. Okay.
So the next topic I want to introduce is stepwise regression. Stepwise regression is a tool that can help us to better select X variables to be included in our regression model. Imagine a situation where you have multiple X variables, maybe 5, maybe 10, or even 20. Then you definitely don't want to include all of them in your regression model because, as we discussed earlier, the more X variables you enter, the higher the R-squared and the more noise you introduce in the model. Not all the 20 X variables will be useful or important in predicting Y. So how do we choose among these 20 variables? Well, the stepwise regression is the answer. It will allow us to pick the most important X variables or the X variables that are most highly correlated with Y.
The basic idea of stepwise regression is in the process, one variable will be entered in the model at a time. And starting from the first variable, that should be the one that is the most important one or the one with the highest correlation coefficient. And then after that X variable is in the model, we're gonna pick in the pool, in the rest of the X variables, the next one that is more relevant. And then we're gonna continue this process until at the point we say that is enough, no more variable will be entered. So there are a couple of steps. Of course, we talk about these steps, but in Minitab, these will be done automatically or behind the scene. We don't really see that. So the first step is to run simple regression model for all the X variables. And then among all the models for all the X variables, the one with the highest R-square will be selected. Then we'll move to the next step, step 2. We have a simple linear regression model with Y and the X variable with the highest R-square. Okay? And the next variable that we'll choose will be the one with the largest significant contribution to the model. Whenever we pick a new variable, we include a new variable in the model. We test all the X variables that are already in the model to make sure they're still highly significant. So we're gonna repeat this process until at the point there's no more X variables that can contribute to the model significantly or no more X variables that turns to be insignificant. Then we stop there. So let's look at this example. It says 10 weekend, the personal manager of the Zerenko pharmaceutical company is interested in forecasting whether a particular applicant will become a good salesperson. She decides to use the first month sales as the dependent variable Y, and she chooses to analyze the following independent variables. Okay, so Y variable will be the month sales, the first month sales, and X variable include selling aptitude test score. X2 is the age in years, X3 the anxiety test score, X4 is the experience in years, and X5 is the high school GPA. Okay, so 5 X variables to run the multiple linear regression model. First of all, let's look at the correlation matrix, just so that we have a general idea of how these variables are correlated with each other. If you look at the first column right here, all of these values are the correlation coefficients for each of the X variables with the Y variable sales, right? So it seems like aptitude score, age, and GPA are good predictors of sales. Their correlation coefficients are relatively high, higher than 0.6. And the next one might be experience. Anxiety score is actually negatively correlated with sales, which kind of makes sense, but it's not a strong correlation. All right. Now, if you move to the next couple of columns, they are the correlation among the X variables. Okay. If any of those numbers is high, that means these two X variables are highly correlated and there's potential multicollinearity issue. By examining all of those numbers, the one I see is this one, age versus GPA. I am not sure why, but somehow age and GPA are highly correlated with 0.695. So we do want to keep that in mind when we run multiple linear regression models. At the end, we want to, if we include these two variables at the same time, we want to double check for multicollinearity. All right, I want to turn to Minitab and show you there how we do this stepwise regression. All right, so here's my Minitab with the data. The name of the data file is called salesperson. The Y variable is the first one, sales. The rest of them are all the X variables. And we want to use stepwise regression to run the multiple linear regression model to get the best model for forecasting purpose or other reference purpose. So let's get started. We're gonna do stat, go to regression again, and pick fit regression model. So it's really the same as before. All right, the response variable will be sales. So double click on sales, we got that. The continuous predictors, we have all continuous predictors. So I highlight all of them and click select. I've picked out variables. You can double click each one to add them as well. Either way works, all right? So before you hit OK, you do want to move to stepwise because we want to use stepwise regression. On the top, you will see method. Right now, the default is none, but we want to pick stepwise, which is the third choice here. So click on stepwise, and you will notice there are two options at the end, alpha to enter, alpha to remove. So these two are the criteria we use to determine under what condition X variable will be added and under what condition an X variable will be moved. Okay, and this is almost like the 0.5% alpha we pick is the significant level, right? So this alpha is the same. The default for Minitab is 0.15. We typically test as 0.05 level. So let me pick 0.05. And of course, the change of this alpha level, it really depends on how stringent you want to be. If I pick 0.15, that basically allows more variables to enter my model. If I pick 0.05, then that basically means I allow fewer variables to enter my model. So that means I require the variable to be very significant, very important to enter my model. So I'm going to pick 0.05 and click OK. Then click OK again to get the results. So there we go. All right. And this is the result for our multiple linear regression model. It turns out among all the X variables we have, 5 of them, only 2 of them eventually entered in our model and stayed there, aptitude score and age. Okay. Both of them are highly significant, as you can tell from the p-value here. And we don't have multicollinearity because VIF is very small, very close to 1. Now, adjusted R-square is pretty good, 88%. Looking at the p-value for the F-test, we can tell the model is valid. So it's pretty good so far. Of course, we didn't check the residues, which we should in practice or to make sure the model is good to use. So that's the stepwise regression. Okay, let me switch back to the document and wrap up this topic. Just a couple of cautions at the end. Number one, stepwise is a nice method that allows us to pick the variables, but it doesn't guarantee that the model you find will be perfect or the best model ever, right? The second potential problem with stepwise is sometimes there could be overfitting. This means when you want to pick the model, you pick the model that fit your data very well, but it may not be a good job when you focused. A better way to do this is really chop your data into 2 sets. Use the first set to run the model and use the second set to test if your model can predict very well. That's a better way. Lastly, when the F-test is significant, it doesn't mean that your model is useful. It only means that your model is valid. And actually, verifying that the model is valid is just the first step. It's a very basic requirement. Then we talk about how well the model fits data. Then we'll talk about which X variables are highly correlated with Y. Do we have other issues? Do we have heteroscedasticity? Do we have multicollinearity? After checking all of those, then we can determine if the model is useful or not. All right. So that's all we have for chapter 7. I'll talk to you next time.